Hi, everybody. Welcome to Lesson 8, which we're going to look at applications of geometric series. So in the last lesson, we developed a formula for the sum of a geometric series, which is S of n equals the first term minus the first term times the common ratio to the n all over 1 minus r. So that's the given formula for the sum of a geometric series. So we're going to be using that today to kind of solve problems that are more application than here's a list of numbers, add them up. But before we get to that, let's take a jump back to exponential functions. So suppose you have $1,000 invested in an account that paid an annual rate of 3.6% compounded monthly. Oh, this is a compounded monthly problem. So hopefully you can think back to January when we came up with that formula, which gives us the amount of money, the amount of total interest earned and the total amount of money in an account that compounds n times a year. So we just need to plug into this formula. I'm starting with $1,000 and I'm just letting it sit there. I'm just letting that money sit there for 1 year. 1 plus r over n, I'm compounding monthly to the n times 1 year. That's going to tell me how much money I have if I just take $1,000 and throw it in a bank account and let it sit there. So I'm growing at 3.6% compounded monthly to the 12 times 1. So I have 1036.60. So 1036.60 cents. That's how much money I would have in my bank account. We're going to change that up here. So look, it looks very similar, but it's actually a really different concept. So $100 is deposited at the end of every month for 12 months. So there's a big difference. I'm not just putting all the money into the account at once. I'm putting money into the account every month. So this is what a lot of people do when they save for retirement. Is what they do is they put money away every paycheck or every two paychecks. They put that money away and let it compound interest. So I'm not just taking all my money and throwing it in the bank at once. I'm putting a little bit of the money at a time in the bank account. So $100 is deposited in an account at the end of every month for 12 months. That earns an annual interest rate of 3.6% compounded monthly. So I have that same idea of 1 plus 0.036 divided by 12, which actually, if you type that into a calculator, comes out to be, just because I'm going to write that nice decimal instead of a crazy fraction each time, 1.003. So that's kind of my multiplier there is 1.003. How much money will be in the account immediately after the last payment? So the first month, I put in $100. Done. That's all that happened. The first month happens and I put in $100. Now, another month goes by, and what happens? Well, this month gains interest. This month here gets that interest. But it's a new month, so I also have to add in $100. So I took my money from the first month, gave it interest. That money got interest there, and then I added $100 to the account. What happens next month? Well, all of this gets interest. This is month 3 here. So this guy is going to get another dose of interest. So 1.003 squared. He got another 1.003. This $100 is going to get its first dose of interest, but it's a new month, so I'm going to add in another $100. Do you see how this is different than up above where I just let the money sit in the account? Here, each month I'm adding a little bit of interest and I'm adding a new $100. So let's go to month 4 now and see what happens. This first $100 that I added is going to get another dose of interest. It was an exponent of 2, now it's an exponent of 3. Next term's going to get another bit of interest. This $100 I just added is going to get its first dose of interest. And it's a new month, so I'm going to add in $100. So look what's happening here. Every month is actually a geometric series. The amount of money sitting in my account each month is a geometric series. Let me write that here. This is a geometric series. where A1 is what I add each month. R is that multiplier, that interest factor. And N is how many terms I'm adding up. How many terms? So at any month, I can say I have $100. I'm using that geometric series formula we developed in the last lesson. 100 minus 100 times R to the N over 1 minus R. This formula tells me the amount of money I've saved up at the end of any month. So if I want, after a year, I need to do S of 12. I need to know how much money is going to be in this account. If I let this pattern keep going on for 12 months, I want to know how much money will I have in a year. It's not going to be too much. I hate to break it to you. So after a year, this is what I need to type into my calculator right now. So let me go to my calculator. Use the fraction button, alpha y equals enter. It's your best friend. 100 minus 100, parentheses, 1.003 to the 12th over 1 minus 1.003. Nope, 3. That's how much money is in my bank account. 1219, I'm going to round it up to 1220. So after a whole year goes by, I have $1,220. So saving for retirement is a geometric series. The amount of money I have at any month along the way of me saving up for this like retirement here is a geometric series. So when Julie was born, her parents invested $2,500 in an account that compounded annually at a rate of 2%. So what's my multiplier here? My multiplier is 1.02. I'm growing by 2% annually. On her birthday every year, her parents invest another $2,500 into this account. Julie is loaded. After she graduates college, her parents will let Julie finally access this money. So write a recursive formula, that's the one with the a sub n's, that model the amount of money in Julie's account after n years. So recursive formulas have two parts. This is a little throwback here. I know it's been a while. It's been a while since we've done recursive formulas, but you got to tell me where to start. And how do I get to the next term? How do I get to the next term? Well, let's think about what we did here. We went to the guy before me and multiplied him with some interest, right? We went to the guy before me and gave it interest. And then we stuck on, in this case, another $2,500. This here's the recursive formula. Give the previous term the interest and then add on whatever you want to add for the amount of money. So use the geometric series formula to write an expression for how much money Julie has in her account after n years. Well, initially, the first month, the monthly payment is $2,500 minus 2,500 times R. That's my ratio, my multiplier, n years over 1 minus n. That's it. Julie will graduate college after her 22nd birthday. How much money is she going to have? Julie's going to be loaded after her 22nd birthday. 2,500 minus 2,500, 1.02 to the 22. I'm just plugging into the geometric series formula here. And now I'm going to go to my calculator. And see what we got. Nope. So alpha y equals enter 2500 minus 2500 parentheses 1.02 raised to the 22 all over 1 minus 1.02 is that much money. Julius got 68,247 68,247.46. That's how much money Julie has in her account after her 22nd birthday. So I know you've missed this. I'll do a quick little side note. Her parents put in 2,500 22 times. So how much money of that is actually her parents' money? 2,500 times 22. Only 55. Whoa. Easy there, Sparky. What happened there, Sparky? I don't know. That was crazy. I'll leave that in there. I won't edit that out. Julie's parents put in $55,000 into the account. But because it was compounding interest, look how much money she actually got. She actually ended up with $68,000 because each year that initial amount got interest and the next amount got interest. So that interest compounds and grows pretty rapidly, which is the beautiful part of this geometric series and this idea of money growing by a percentage. All right, so here's a formula. It's really the geometric series formula. So I'm going to kind of cross this out here. We're used to working with this. It's the geometric series formula, just kind of reworked. But one thing I do want to point out is, notice how both of these have an A1. In this formula, they factored it out. So this is where they're getting, this is another formula you might see me using a little bit, is that A1, I might factor it out, but it doesn't matter in the end. It doesn't matter in the end. So find the interest earned and the future value of an annuity with a monthly payment of $200 for 2 years in an account that pays 6% compounded monthly. So an annuity is a geometric series. That's where you're putting the money in each month. So each month I'm putting in $200. That's month one. The next month, that $200 gets interest. It gets 6% compounded monthly. So that's my multiplier. But it's a new month, so I have to add another $200. That's the pattern that keeps happening. Now I'm going to do it again. Everybody's going to get another dose of interest that was already there. That gets interest again. This guy's getting interest for the first time. And it's a new month, so I'm adding in $200. So hopefully you notice this is a geometric series. 2 years is going to be how many payments? It's going to be 24 payments that happen. So the sum of the first 24 terms is 200 minus 200 times the ratio to the n all over 1 minus the ratio. So that's what I need to type in my calculator. Above, I just had a kind of a simplified formula, but I want you guys just practicing using this geometric series formula here. So let's see what we got. We've got alpha y equals, enter, 200 minus 200 parentheses, 1 plus 0.06 divided by 12, close it. 24 months went by, 1 minus parentheses 1 plus 0.06 divided by 12. This is going to tell me how much money I have in my account. $5,086.39. So the sum is $5,086.39. Did I say? Yes. 39 cents. That's how much money is ending up in this account. So when you see these annuity, these retirement type saving problems, it's a geometric series that we're going to use. How much money would need to be invested every month into an account with an annual rate of 12% compounded monthly in order to have $3,000 after 18 months? So notice, I don't know what I'm putting in each month. I know it has to equal, I know the series equals $3,000. So here, I want to solve for that A1, that initial amount, that thing I keep adding each month. So that's why I'm going to use this version of the formula. A1, that initial amount, minus, actually, I'll use the formula that I gave you the first time. The ratio is 12% compounded monthly. 18 months went by. All over 1 minus the ratio. So let's clean up that denominator there. Let's clean up that denominator. 1 minus parentheses 1 plus 0.12 divided by 12 is negative 0.01. So what's really on the bottom down here is negative 0.01. So to solve this, I'm going to multiply that up. I'm going to multiply both sides by negative 0.01. So I need to do 3,000 times negative 0.01, which gives me negative 30. So negative 30, and I'm going to factor out that a1 there. 1 minus 1 plus 0.12 over 12 to the 18. So a1 so negative 30 equals a1 times that. So let me see what that is. 1 minus parentheses 1 plus 0.12 divided by 12 to the 18. So that's what's next to my a1 there. That's a1 times that crazy decimal. So I need to divide that term over to get a1. So negative 30 divided by that crazy decimal I just got, second answer, tells me how much money should I be putting away each month? $152.95. $152.95. That's how much money I need to put away each month. So to review that, I plugged it into the geometric series formula, but I didn't know the first term. I didn't know what the monthly payment was. So I multiplied up the denominator to clean that out. Then I factored out that a1, so I only had one variable to deal with. I typed this bad boy into my calculator and then divided him over. The algebra is not terrible, it just looks a little bit frightening. So Mr. Hines invests $100 into a structured savings plan a month for when he retires 40 years from now. Can't wait. It earns 6% interest compounded monthly. How much money will he have when I retire? How much money am I going to have when I retire 40 years from now after I teach your grandchildren? So I invest $100 a month. So the sum equals $100 a month, 6% compounded monthly. 6% compounded monthly. That's that interest rate, 6% divided by 12. To the n, how many months go by? Well, 40 years, how many more months of work do I have? Well, 40 times 12 would be, I have to work 480 more months. Divided by 1 minus that common ratio, divided by that multiplier. This expression will tell me how much money I would have in this scenario. If I put $100 away a month, how much money will I have when I retire? Let's make a fraction. 100 minus 100 parentheses 1 plus 0.06 divided by 12 to the 480 months I have to work. Oh goodness, that's frightening to think about. 1 minus the common ratio. I hit enter, and that's how much money I would have in my savings account if I just let it sit there and I put $100 in each month. I'd have $149,149, and can't forget those 7 cents. That's how much money I would have in my savings account 40 years from now. Here's the crazy awesome part. How much money of that's mine? Well, I put $100 away 480 times. So how much money of that is actually mine? Only $48,000 is my money. The rest of that money grew from that compounding interest. And this is why you guys need to start saving money the minute you get a job. When you're in your 20s working, don't think you can just spend all your money you want. You have to start saving early, because under this scenario, $48,000 became $199,000. It almost quadrupled, it more than quadrupled in its value. That's awesome. That is an awesome thing that happens. Determine the amount of money Mr. Hines should put into an annuity each month so he can retire with $1 million saved. I want to have $1 million. I want to be a millionaire when I retire. So that's the sum. I know it equals $1 million. I don't know. We're changing the $100 a month. I don't know how much I'm putting away each month. Everything else is staying the same, though. I'm still retiring 40 years from now. I'm still compounding at that same interest rate. The only thing that changed is I'm equaling $1 million. I don't know how much money I have. So we solve it just like we did above. I clean up that denominator. I'm going to figure out what this denominator is and multiply it up. So 1 minus parentheses 1 plus 0.06 divided by 12. And I'm going to multiply that by $1 million, by 1 million. So that's what's on the other side of the equation. 1, 2, 3, 1, 2, 3. Negative 5,000. So I'm gonna I figured out what it was and I multiplied it up. So negative 5,000 equals, factor out that A1, factor it out. So 1 minus 1 plus 0.06 to the 12 to the 480. So now I can type this crazy expression in and divide it over. 1 minus parentheses 1 plus 0.06 divided by 12, close it to the 480. That's what's on the other side. So negative 5,000 equals A1 times that. So I need to do negative 5,000 divided by 5,000 divided by that answer. And that gives me how much I need each month. I would need to put away $502.14 each month. That's how much money I would need to put away each month to be a millionaire when I retire under these scenarios. So I want you guys to realize, we're going to skip 6, we're going to move on from that. I want you guys to realize this geometric series formula has a ton of real life applications. In the next lesson, we're going to be buying houses and cars and college loans and stuff. This geometric series formula is powerful and actually affects your life, whether you want it to or not. So try the homework, and I'll see you guys in the next lesson.